going to be looking at energy. So this is the first part of your physics paper 1, and it makes up quite a large part. Now, the reality about today and about energy just as a whole is that it is really heavy on the calculations, and we're going to make sure today that we've got a really good procedure for what we're doing there and how we are going to maximize our marks in the exam. Now, you'll see there are two kind of keys as we go through. If your exam is highlighted in green, it means this is content that you can be assessed in. However, if this is grayed out, it means that this is content that you will not be assessed on. So, for example, if we start to have a look at the first bit of information, on every single slide that we look at today, there's going to be a key on the bottom right-hand side. So we've got Combined Science Foundation, Combined Science Higher, Separate Science Foundation, and Separate Science Higher. So I say right at the beginning, kind of pinpoint, right, which is my exam. I'll point it out as we go through as well, but we need to kind of match up, right, is this something that I need to worry about for my exam or not? Now, actually, one thing I'd say for the energy, everything that we're going to look at today is entirely on every single paper. So it doesn't matter if you're doing Combined Science Foundation or Separate Science Higher. All the content within this section around energy will be on your exams. With this, what I would say is that we're not going to look at the required practicals today. So in this section of energy, the required practicals won't feature. They'll be collected together in a separate video and in a separate lesson later on in the sequence. So today we're just looking at the theory. We're going to avoid the required practicals in their entirety, but we will be coming back to them. So first of all, when we talk about energy, there's this first kind of key word on the specification about system. Now, if we ever refer to a system in physics, it is really just an object or group of objects. Be aware of it. They might use the word, but it is very unlikely that you're going to get asked what it means. But it's just the idea in physics, we're going to refer to objects or groups of them. And when we do so, it's a reference to a system. Where this fits into energy is that when we have a system changing, and we'll look at some examples of this, the way the energy is physically stored can also be changed. And that's where energy transfers start to come into this. What we're going to be focusing on the first section of energy is really looking at different energy changes and how we describe them. But whenever we have an object, kind of that system change, the energy store may change with that. Now, there are different energy stores, and some of them, in all honesty, feature more in paper 2 than they do in paper 1. So we have a magnetic energy store, and this is not going to get touched on in paper 1. Now, this is the energy that's stored when we've got attracting poles or repelling poles interacting. So actually, attracting poles will be pulled apart, or pulled together, I should say, while repelling poles are going to be pushed away from each other. So we've got that attraction and we've got that repulsion. So attracting poles will be pulled together and repelling poles will be pushed apart. So there's a good little typo in there. Now, internal energy is the total kinetic and potential energy of particles in an object. And we look at this very much when we're focusing on particle model later on within the physics topic. We also have chemical energy, and this is the energy that's stored in chemical bonds. So there's a lot more of that within chemistry than anything else. Kinetic energy is the energy of a moving object. So anything that's moving in its entirety has got, or even in part, has got kinetic energy. While gravitational potential is the energy that we store in an object at a height. So as soon as anything's lifted off the ground, you're going to have an increase in gravitational potential energy. The higher it's lifted, the more gravitational potential energy the object or system is going to have. We also have elastic potential, and this is any energy stored when an object is either stretched or compressed. Because when we release that force that's causing the stretch or compression, we're going to see a change to that system, normally in that it's going to move. Now, these three energy stores are going to make up a huge portion of the energy topic. And It's why there's an equation that we need to use for kinetic energy, for gravitational potential, and also elastic potential also. We have nuclear energy too. Now this is the energy that's stored in the nucleus of an atom, and that more will get tested when we look at radioactivity and later on within the paper. And again, this tends to lean into the separate science content when we look at fission, but it doesn't mean that actually as combined science you don't need to know that we do have nuclear energy, and that is the energy stored within an atom. We then finally have electrostatic. Now with this is when we've got the idea that we've got attracting or repelling forces brought together due to different charges that they may have. So that idea that positive charges will repel each other, negative will repel, or positive and negative will attract. Again, it features on both. It's kind of you need to know about electrostatic energy stores, but it more sits in the separate science paper when you look at electricity and that idea of static electricity. So the main idea here then is that energy can be moved from one store to another by either work and by heat. So we can have this transfer occur. So if we look at this then, we've got different energy stores. Now, some energy forms can't be stored. And the different ones here that we've got is electrical current. So we can have energy transferred through electrical current, but it won't be stored in any way. Same with light, same with sound, and same with thermal. So yes, they're examples of energy, but these are not energy stores. So if we have a look, we've got some different scenarios that have been outlined and highlighted by the exam board as you need to know. And it does mean that when they look at the context of exam questions, these are the ones that they're going to bring up. So we've got, for example, an object projected upwards. You need to be able to describe the energy change that's happening with this. So in this, as we have an object projected upwards, originally actually the person would have had a store of chemical energy that's then thrown that up, it's been transferred into kinetic, and what we'll find is that as it rises higher and higher and higher, it will actually slow down, and that energy will be stored into gravitational potential energy. So as this gets higher, it will have less kinetic and should in theory have more gravitational potential. Another scenario that AQA give is that idea that we have a moving object hitting an obstacle. Now in this, we'll have kinetic energy going in again, but this time is going to be transferred, and it can be transferred, not stored, but transferred as sound waves, and we're also going to get some thermal energy from this as well. So we'll hear it and there'll be a temperature increase in the surroundings too. We've also got objects accelerated by constant force, and this depends on the context. It either tends to be objects that have got like a fuel supply that's wrong on the earth, or it could include something that's falling due to gravity. So in this scenario, we've got an object accelerated by a constant force. So in this one, we've got chemical energy, that fuel going in, storing this chemical energy, and this has been transferred into kinetic energy. However, if this object is falling, it is still being accelerated by a constant force. So gravity now is the force acting downwards, causing that acceleration. Now with falling, what's going to happen here is gravitational potential energy will be transferred into kinetic energy. And for a lot of the calculations that we use in this exam, we can assume that if we know the original GPE of the object, we can find its kinetic energy, assuming that all of that gravitational potential energy is transferred into kinetic. Now that's theoretical, because the reality is that when we have any object fall, there will be friction, and actually a little bit of that energy, if not a lot of it, might be dissipated and transferred as thermal energy instead. But for a lot of the equations that we can use, you might, for like a 5-6 mark on a higher paper, need to combine and use gravitational potential and kinetic. But what we're doing here is assuming that all of the gravitational potential is transferred into kinetic as an object falls. We also have a vehicle slowing down. So we've got vehicles or objects crashing. We've got vehicles slowing down. So in here, we've got back to that kinetic energy, and this is going to be transferred into thermal energy. So brakes are going to tend to get hotter as this happens. You may also have a bit of sound. You may be able to hear like the screech of the brakes. As another one, we've got bringing water to boil in an electric circuit. Now, it's not an energy store going into this because electric cannot be stored, but we do have an electric current, and that will be transferred into thermal energy. So we're going from electricity into heat. So we're going to spend a little bit of time looking at the different equations linked to kinetic energy, linked into gravitational potential, and linked into elastic potential. So as a general definition, kinetic energy is the energy that any moving object has. The faster something is moving, the more kinetic energy it has. Now there is an equation that you need to be able to use to calculate kinetic energy. Now the equation here will be kinetic energy equals half times mass times by speed squared. Common mistakes that you see when you're marking these is that people forget to do the squared. That tends to be the little common mistake that happens. Even if you've written the equation incorrectly, it tends to get dropped as you go. So I'd say just be vigilant that actually you've taken every single aspect you're working through. Now you can either, when you're writing your equations, write it out in full, or you can write in the simple equation. That choice is yours, whichever one you feel kind of most confident with. But I'd say start by learning your word equations with this first of all, before you then learn the symbols for them instead. One thing that's vital for your physics exam is knowing your units inside and out, because that's going to help you identify and use the correct equations that are actually required for this. So anything to do with energy is measured in joules, mass is measured in kilograms, and speed is measured in meters per second. Always be on the lookout when you're doing your exam questions that unit conversions are something to kind of be aware of. Generally speaking, if you do notice like multiple letters, so for example like kilojoules or megajoules, that would be a giveaway that there might be a unit conversion. Kilograms is fine. That's actually one of the rare ones where actually multiple letters for like a standard unit is all right. So again, if you see like grams for mass, that should be a little alarm bell of I need to do a unit conversion. That will tend on a foundation paper to appear kind of later on if it occurs. While on a higher paper, you can expect that to occur from literally first exam question on a calculation onwards. So just get into that habit of looking for unit conversions where they are. I say there's a nice kind of trick around this. Have your values on one side and like as flashcards and units on the other to really be like a really like critical bit to kind of revise and make sure you're aware of and confident with. So we have a look at word examples, a few of these as we go through this workshop. So in this, we've got a 750 gram book that's thrown and has an initial speed of 12 meters per second. And we're asked to find its kinetic energy. So marks here are 4. Now that kind of gives an indication of that there might be unit conversion in here and there might be some extra processing we need to do. So with this, first of all, as general advice as you're going through, highlight all numbers you get given for calculations. It just helps that number kind of pop off the sheet of paper, so it makes it easier to kind of access, right, what numbers do I need to use and where they're going to go. But the first thing once you've done that and you've highlighted your values is look for any of your unit conversions. Now on this one, we've got 750 grams and we'll need to convert that into kilograms before we even get started. So here we've got 750 grams, we'll divide that by 1,000 and turn that into 0.75. Be really systematic in your exam questions. Some of the questions might just ask you for the equation first of all and write it in the space. Later on, especially in a higher paper, they'll just ask you to calculate, but it doesn't really matter. If you aren't given the formula, write your formula first of all. I've just make it fit here, done the simple one, but for example, just kinetic energy equals half times mass times speed or velocity squared will be absolutely fine here. But always make sure you've started by writing your equation. You are then going to get marks for substituting correctly. Always make sure that you put your numbers in before you go to do any possible rearrangements that might be needed. So find your equation, then substitute. Now in here, I would try and write this directly underneath. So that idea of our kinetic energy equals half times our mass that we found to be 0.75, and I'm going to times that by 12 squared. At that point, if you need to rearrange, you can then go on and do so. And it's actually easier to rearrange with numbers rather than words. It makes it less abstract, so you're less likely to make a mistake. Now on this one, there's no substitution that's needed. So in this, we can just put straight in. I've kind of broken it down. I know that I've got a bit of a tendency to misuse my calculator and not square this correctly. So I'd kind of do my interim step and then go full through and find my final answer. But that's a personal choice. You could just put that straight into your calculator. If you know that actually you generally get it right and that you do, just go straight in, and you don't need to show the interim kind of mark there that I've done. Always keep an eye out for AQA that you know if they want you to round the answer or not. They'll always give an instruction. They might say, give this in standard form. They might say, write this to 2 significant figures. If they want you to do anything, they'll give you an instruction. If not, you can just write the answer exactly as it is from your calculator. If you choose to round it or not from that point is your own kind of choosing. But you can choose to, you can choose not to. What I would say is just always make sure that when you have rounded, go back and double check your work, because it is unbelievable how often you see people making very simple rounding errors just down to the stress of the exam at the time. So take your time with it. Moving on then, we've got elastic potential energy. Now this is the energy that's stored when an object is either stretched or when it's compressed. The equation for this is elastic potential energy is half times spring constant times by extension squared. And again, same advice as before, know your units. So our energy will be in joules, spring constant is in Newton meters, and extension will be in meters squared. So that will give us our elastic potential. So that one's a little bit more of an unusual one to record as your unit. Again, be prepared that unit conversions could and will happen at some point in your paper. If we have a look at this example, we've got a spring with a spring constant of 1.2 Newton meters that is stretched 22 centimeters. Find its elastic potential energy. So in this, we'll notice the same kind of structure. We'll highlight our values, find any unit conversions. Generally, there might tend to be 1. 2's rare, but it could happen. So just because you found 1 doesn't mean there might not be another. It's unlikely, but be vigilant and look out for them. In this one, we've got 22 centimeters. So we'll divide this by 100 to turn it into meters, and we'll then continue by writing down our formula. So if we're needing to find elastic potential energy, well, that equals half times spring constant times by extension squared. At that point, we'll then go and substitute, trying to keep everything really logically directly below our previous bit of work. So we've got half times 1.2 times the 0.22 squared. Then again, I'll always choose to do that interim step and just show what that is squared, but again, a personal choice. You can just put that straight into calculator and off you go. Now, I have rounded this, but if there wasn't an instruction in the question, you don't need to. I've taken it to 2 significant figures because that's what was given in the question, but actually stopping there would be enough. Unless they had specified give it to 2 significant figures, you could just stop there and you then don't have to go any further. With gravitational potential then, this is our energy stored in an object at a height. Our equation is going to be mass times gravitational field strength times by height. With this again, no units, so GPE is in joules, mass is in kilograms, gravitational field strength is in Newton kilograms, and height is in meters. Now, typically, a lot of the exam questions are going to refer to gravitational field strength as 9.8. They might even use 9.81, but it will be a number that I'm sure doing mock practice, you'll notice in papers comes up a lot. So they will give this. They don't expect you to recall it. So the other thing is that actually mass times gravitational field strength equals weight. So these two values multiplied together is the weight of an object. So our weight is dependent on mass and the strength of gravity. So it does mean we tend to weigh different amounts if we were on different planets, for example. So if you are given weight and height, it does mean that you could just multiply weight by height to find out your GPE. So if we have a look, here's an example of what might come up. So I'll normally give a bit more context, but the system of how we're going to approach this is the same. So we'll convert our units. In this case, it was the 350 that we've divided to get into kilograms. We'll write down our formula exactly as it is. We won't worry about rearrangement. We'll just write it exactly as it is. We'll then substitute, putting our values directly below, and we'll then go through to do our calculation. So if you do need to rearrange, it is at this point you would do it. Again, they haven't given any instructions, so you could leave this exactly as it is, or if you'd rather, you can round it. But if you're going to do that, follow their number of significant figures they've used. But to be honest, it just gives you more of a tripping point. Unless they say round it, I would just leave it as it is. In this one, we're going to have a look at a rearrangement, as it can tend to be a little bit tricky, but just be really procedural, step by step with it. So in this question, same process. We're going to do a unit conversion, and we'll times this now by 1,000 to turn it into joules. We'll write down our equation, and we'll substitute. Now for me, some people are really confident they'll do m equals this divided by these two things combined. I know I tend to make mistakes, so I do go a little bit slower. So for example, I'll do this equals m, and I'll find what those two numbers are multiplied together. I will then take this times across the equal sign, becoming a divide, giving me overall a mass of this. Just be careful when you do go to write your answer. Some people, and it's down to the pressure of exams, might just write 15.5 and kind of leave it there and stop writing. Don't truncate, which is like just stop short. Do actually write down the full answer you get from your calculator, just in the event that maybe they did want you to round, or you make a rounding error, that you don't get penalised for it like too many times. So show the full answer that's coming from your calculator before you round. You really need to lead the examiner by the hand of your thought process and how you went about this. So we'll look at this when we focus on required practicals in a bit more detail. But we have this idea about specific heat capacity. Now, it is a very common definition that comes up, and they're going to be pedantic. It's normally 2 marks. In this, it is the idea that we need, well, specific heat capacity is the amount of energy that's needed to raise an object's temperature by a degree, provided the object is 1 kilogram. So I've got a 1 kilogram substance. It is the energy needed to raise its temperature by 1 degree C. And the specificity there is the idea about 1 kilogram and the 1 degree Celsius. Now, we have an equation for this. You don't need to learn it in any way, but you do need to be able to use it. So we've got change in thermal energy is equal to mass times specific heat capacity times by temperature change. Now, this does appear and can get used a bit later on when we look at particle model and density a bit later on in latent heat. So it does tend to actually get quite heavily assessed when we're using this calculation. And it does tend to be a few more marks, because often what they'll do is they will give you like a start and end temperature. So you'll need to figure out what the actual temperature change was. Because of that, it does tend to mean that these calculations might be 4 or 5 marks rather than 2 or 3. But we've still got our change in thermal energies in joules. Mass is still in kilograms, and specific heat capacity, I wouldn't kind of anticipate you're going to be asked for the equation, is joules per kilogram degree C, and temperature change is in degree C. If you struggle to learn that as a unit, just to kind of point out, this unit is all of these 3 combined. So it is telling us we'll do joules divided by these 2 multiplied together. So provided you know your other units, you've got a way of kind of retrieving that one if you're ever asked to give it. But as of yet, I've actually not seen an exam question where you were asked to give that as a unit. But it is worth being aware of. So if we have a look, we're asked to calculate the energy needed to increase the temperature of 200 grams of gold by 10 degrees. Just be aware that maybe they might say from 0 to 10. So you need to find your temperature change. And we're given the specific heat capacity. The process is exactly the same. We'll just need to make sure we're really looking for unit conversions and we're very clear on what the temperature change is. Like if they've said, for example, it goes from like 71 to 89, we need to find the difference between those two numbers. So we'll convert units. So our grams will get turned into kilograms. We'll write down our full equation. So our specific heat capacity, or energy, I should say, is equal to mass times specific heat capacity times by temperature change. And we'll put in our values. So we've got our mass, we've got our specific heat capacity, and we've got our temperature change in there. And you may have to do a smaller little 1-mark calculation to find that. All values into our calculator, and at this point we're looking at 258 joules to do this. Last equation, I say this, there's efficiency later, but the other equation is power. Now power comes up in electricity as well. We're going to focus on power in terms of energy, and it's the rate at which energy is transferred, or it is the rate at which work is done. Because actually, energy transferred and work done are the same thing. So power equals energy transferred divided by time. And there's our little shortened equation. Power is now measured in watts, energy still in joules, and time is in seconds. But energy transferred is equal to work done. So what this does mean is that power is also equal to work done over time. So it's kind of two equations in one. But both of these equations are joules divided by seconds. So work done is measured in joules, as is energy transferred. And they are both joules divided by seconds to find our power. So both of these equations are exactly the same. You'll take your energy and divide by time. What's worth mentioning, this might be a small little 1 marker that comes up, is that if we are transferring 1 joule per second, this is the equivalent to a watt. So 1 watt is 1 joule being transferred every second. So if they've been mean, and this will more start to appear on higher papers, they might start to give values in standard form. And it just adds that extra bit of challenge, making sure that you're confident in how to use your calculator and do some calculations with larger values. So in this one, the electrical generators can provide 1.5 times 10 to the power 9 watts of power for a maximum of 5 hours. Calculate the energy transferred. So in this, we'll find our unit conversion. Hours into seconds, not the nicest. You need to times by 60 to get into minutes, and then times by 60 again. We'll write down our formula, and we'll then do our substitution. And in this case, we're going to have to rearrange. So here we'll have our energy is equal to this times by 18,000. In a question like this, they're incredibly likely to ask you to give your answer in standard form. So always look out for those extra instructions they may give. That leads us on then to the second part of this with energy, where it's looking at energy transfers in the system, but starting to focus on the efficiency behind this. So we've got this idea about the law of conservation of energy. And this is the fundamental rule that energy cannot be created or destroyed. So there's no other reference in any of our science exams to energy being made. It just cannot happen. So energy cannot be created or destroyed. It can only be transferred, and that might be either usefully or dissipated in that it's not been a useful energy transfer. So what it does mean is that whenever we're kind of looking at an energy transfer, whatever's gone in has to come out. It might not be useful, but it has to come out. So what we find then is that in all systems, energy is dissipated, in that we're not using the energy in a useful way. It's not how we intended for it to come out. So, for example, if we're looking at a television, we want the energy to be transferred from electrical energy into light and sound. However, any electrical device tends to get hot. That's not the intention of using a television. That's not the energy transfer we wanted. So that's an example of energy being transferred in a not useful way at all. So this TV will waste as thermal energy. And a lot of things, even if they're meant to be heating, will waste energy as thermal energy. So energy does tend to get dissipated in that it gets transferred in a non-useful way to the environment. And it will just over time dissipate and actually be released into the environment and appear to disappear. It will spread out and go. So in a lot of things, we're going to find that energy is dissipated as heat. So we're going to transfer this not useful and it'll go to thermal. It will raise the surrounding temperatures and eventually just dissipate and transfer to the surroundings over time. This is not accessible to us, so it's not been stored in a useful way. It's not a store. So we've got an inaccessible thermal kind of store of energy, but it's gone. That thermal energy is gone. It's not useful to us. Now, one aspect of this is we need to be able to talk about how we may reduce this. And there are two main ideas. We've got lubrication, so that's reducing friction. As friction is one big way in which energy gets transferred, not usefully as heat. And we've also got the idea of insulation. So with lubricants, the idea here is reduce friction between surfaces. The surfaces should now slide more smoothly over each other, and as a result, we should have less energy wasted as heat, but also less energy dissipated as sound as well. So it should just be a smoother kind of process of those surfaces sliding. With thermal insulation, so loft insulation, carpets, the cavity wall stuff, all of these are designed to have an insulator within them. That's normally air pockets, which is a really poor insulator. And what it does is it reduces the transfer of energy through. So air that's trapped in these little pockets within the materials is a really bad conductor, trapping the energy in and reduces its transfer away. The opposite of this, though, is some materials are very good conductors of heat. And there are some examples of questions that have come up in the past where we've tested the conductivity. So good conductors will allow energy to transfer them pretty rapidly. So good conductors have a high thermal conductivity, and they will transfer energy through thermal energy much quicker than an insulator. And one of the ways we can test this is we can have, for example, like different metal rods of different materials, and we can have something heating an end. And what will often happen is we may attach like a ball of wax that will melt when it gets hot at a fixed distance away. And we can see the best conductor by which one has the wax drop off first. One thing that might happen, especially if they're making links to applying a knowledge, is that this insulation and the idea about energy loss and heat loss in particular can be linked to our homes. And so we've got different ways that we can affect the rate of cooling or energy loss in a building. So if our walls are thicker, it's going to reduce the loss of temperature. The thermal conductivity of the walls as well. So we actually don't use building materials that are good conductors. We want to trap that heat in. The insulation that might be in that building as well. So the higher the insulation, the slower the cooling of that building will happen. Glazing. So triple glazing means that we've got 3 panes of glass with air trapped in between each one. This is going to reduce conduction because that air in between those panels is a really good insulator. We can use draft excluders, those things that kind of get wedged up against the bottom of a door as well. With this then, it kind of links to this idea of efficiency. So if we know that energy in is equal to energy out, not all of that will necessarily be useful. And efficiency is the idea about how much of the energy supplied was actually transferred usefully. There's a couple of equations for this, but with efficiency, it is basically, when we're looking at our equation, the useful divided by the total that went in. So what was used usefully divided by that total. Now this could either be in watts or in joules. So it could be useful power in, or I should say useful power divided by the total power in, or it could be useful energy divided by the total energy in. But it's basically, whatever your efficiency is, you're doing a useful divided by the total that went into this. So if we have a look, the total power input to a solar cell is 2.4 watts when the efficiency is 0.2, so it's 20% efficient. Calculate the useful power output of the solar cell. So with this, we've got our efficiency is equal to useful divided by what went in. So in this case, I've got 0.2 is equal to useful times by 2.4, which is going to give me my useful output would have been 0.48 watts, which is a very small portion of the original 2.4 that went into this. The final section of our energy topic is knowing about different energy resources. Now, this could be linked into talking about the environmental impact, or they could even start to link this possibly into calculations using kinetic energy, for example, or talk about your energy transfers. So fuels fall into two categories. They can either be non-renewable or renewable, and we'll start with our non-renewables first. Our non-renewable resources are ones that are basically used up quicker than they can be replaced. And that means once they're gone, they can't be replaced. The two big examples here is fossil fuels and nuclear. So fossil fuels include coal, oil and natural gas, while I've got nuclear that is also non-renewable. This isn't much a bigger supply though, so it's not so much of a concern about running out as these three currently are. So these have all formed from life from millions of years ago. So those dead organisms that didn't decay in a kind of conventional way and have been preserved for millions of years. Renewable resources, in contrast, are those that are basically replaced at the rate at which they've been used. So they're not under any risk of running out. With energy overall, whether it's renewable or non-renewable, there are three main ways that as a population we use our energy. We use it for heating, electricity, and for transport. Electricity, for the most part, will connect to the national grid that we'll look at in the electricity topic. But for the most part, most power stations will have something causing a voltage by wire spinning near a magnet. And what we'll generally get is we're going to have turbines turning to generate electricity. But it doesn't necessarily have to be coal fueling this. We can have different kinds of energy turning these turbines to turn the generators to generate electricity. And we'll look at some of these now. So with fossil fuels, these are hugely used in power stations. And the reason behind this is that they are incredibly reliable. However, fossil fuels produce greenhouse gases which contribute towards global warming. And that's the huge kind of drawback from each of these. That, and they're also non-renewable, so they are going to run out eventually. In contrast, nuclear fuel is also non-renewable and is incredibly reliable. It doesn't produce greenhouse gases, so there's no contribution towards global warming at all. And actually, nuclear fuel, gram for gram, will release more energy per kilogram of fuel than coal will. However, there is the concerns around safety of this. We're going to find that, yes, there's no climate change concerns because we haven't got greenhouse gases produced, but it is producing radioactive waste. And actually, it's not as quite responsive as our fossil fuel power stations are. It takes a long time to get our power station kind of started up. And also we're going to find that when that power station comes to the end of its life, that's going to cost quite a lot of money to decommission it and get rid of it. Renewable wise, we've got solar, hydroelectric, geothermal, biomass, wind, wave and tidal. With our renewables, huge bonus is they are not about to run out. With biofuel, so this is when we burn plant material that's been more recently grown. It is reliable. We know that wood and plants will burn and when we expect them to, and it is also carbon neutral. The argument here is that if we've got this biomass, maybe we grew it 10 years ago, it removed carbon dioxide 10 years ago, and it released that CO2 back. That's very different towards burning a piece of coal where we're releasing CO2 that was taken out of the Earth's atmosphere millions of years ago. And that's where that kind of difference lies. The problem, however, and this is something that more hits into biology, is that land is a scarce resource. So if we're growing plants to then burn for our energy, we're using land that could be used for something else, and that does cause an issue. We typically use this though for generating electricity, heating, and we can use it for transport as well. That wouldn't be wood. There's some oils, for example, that some cars have been built to use. We also have wind. So this is now where we've got the kinetic energy from the particles in the air causing movement in the turbine. The advantages of renewable energy is that it doesn't produce greenhouse gases, and so it's not going to contribute towards global warming. However, the problems are that it's actually unreliable. And so, for example, when there's no wind, it's just not going to work. And there's also an issue of visual pollution. We typically use wind for electricity generation, and this can feed into the national grid. We also have hydroelectricity. Now again, as an advantage, this is renewable, but it also, like our other renewables, is not producing greenhouse gases, and so will not contribute in any way towards global warming. You'll start to notice a bit of a theme with some of these. However, a problem is that if there is a drought, this can be affected by it, because it relies on having a store of water up high that's then released, and it transfers the GPE into kinetic, causing us to move down to a lower level. Also, for hydroelectricity to work, we need really large reservoirs of water, and so this might actually involve flooding areas and have a loss of habitat. Now, we typically use hydroelectricity to again feed into the national grid, and we use this for electricity generation. Geothermal is another renewable energy resource, and it's incredibly reliable. Provided we have the right site for this, it's a reliable energy resource. Also, it's not going to produce greenhouse gases and so has no contribution at all to global warming. However, it is incredibly expensive. Only certain places will work also, and so not every site will be actually viable for geothermal. We use this for electricity generation, but can also use it for heating. Tidal is another form of renewable energy, and in this we have got the tides moving in and out that turn turbines as they do. The tide is incredibly reliable, it'll go in and out twice a day. And also we're going to find that it does not produce any greenhouse gases, and so also will not contribute towards global warming. However, this has the ability to affect habitats, so river estuaries and around coastlines where we'd find these. It's going to affect the animals and organisms that live in that area because they now have turbines within the water itself. We typically use this for electricity generation also. Solar energy is not going to be any contributor at all to greenhouse gases and so will not cause global warming. However, solar energy is quite unreliable. It doesn't work at night, and during the winter months it will not have as much energy kind of transferred there either. So it does mean that in winter time we're going to generate less electricity. Also, we're going to need huge areas to actually generate adequate electricity for this to be something that we can rely on more solidly than we currently do. We typically do use this though for generating electricity, and we use it for heating also. Water waves are now harnessing the kinetic energy at the sea's wave surface. It does not produce greenhouse gases and therefore has no effect also on global warming. And as a bonus, it's renewable like the others, and so it won't run out. But it, like tidal, is going to involve being placed on coastlines and has the ability to affect habitats. They can also be affected by storms, which can get quite expensive and difficult to repair. And it also, like wind turbines, does not produce a constant supply of electricity. So it's not particularly reliable. But we use this for electricity generation also. So energy resources can either be renewable or non-renewable. They also tend to be reliable or unreliable. Our reliables are our fossil fuels, and it's why we use them so heavily when we look at the production within our power stations, along with nuclear. Yes, they're non-renewable, but they're incredibly reliable. Biofuel also is reliable, as is geothermal. If we have the right site, we know that this is going to work on demand when we need it to. However, in the unreliable section, we've got solar and we've got wind, because the solar, we kind of know it's not going to work at certain points of the year and certain points of the day, such as like nighttime, but also it's very weather dependent. If it's a cloudy day, you're not going to generate as much electricity. Wind turbines, yes, they can work 24 hours a day now, but again, they're only going to work at particular times when the wind levels are just right and in the correct direction. So these are relatively unpredictable, and they're not as reliable as the other energy resources might be. Hydroelectricity, generally reliable, as is tidal, because we know that the tide is going to go in and out at certain points of the day. So these resources are always available and they're readily reliable too. That brings us to the end of energy. We'll be looking at electricity in our next topic.